The solutions of a general trinomial equation can be given in terms of generalized hypergeometric functions. This is basically an expansion on the stuff that I covered at the end of my last quintic video, where we had the Bring-Jerrard quintic. It was a quintic trinomial, and I'm going to look at this more in detail and generalize it to an arbitrary trinomial equation. Of course, we're going to take m and n to be positive integers and also non-zero a and b, so this eliminates cases of binomials or simpler to solve reduced equations. And it's also monic. We have coefficient of 1 for the leading term. Now, if you didn't see the previous video, it might help a little bit, at least towards the end, but we're going to use generalized hypergeometric functions. They have this specific series representation shown here, and we use this ratio of consecutive terms in terms of this rational function to basically rewrite it later on. And also we're going to use Lagrange reversion theorem for the reversion of series as shown here. So first, we're going to start by letting x be equal to minus a to the 1 over m times y. So what this is going to turn our equation into is going to turn it into this, and then we can basically divide out and these things will cancel out, so that we're going to get this more canonical form of y to the n plus m minus y to the n plus t is equal to 0, where we have that t is simply equal to minus a to the minus n plus m over m times b. Okay, now I'm going to rewrite it a little bit further. We're going to get y to the n is equal to t plus y to the n plus m, and now this is almost in the same form as for Lagrange reversion theorem. We're going to do one more substitution. We're going to let z be equal to y to the n, which means that y is equal to mu times z to the 1 over n. And mu is just an nth root of unity. So we get as follows from Lagrange reversion theorem, or sorry, we're first going to have it as z is equal to t plus mu to the m z to the n plus m over n. And now we can apply Lagrange reversion theorem. It has the right form. We have f of z is equal to z to the n plus m over n, and g of z is just mu z to the 1 over n. Okay, so as follows. Again, because the nth roots of unity, these are n solutions, so y1 to yn. Now for the nth derivative of a power function, you could just generally look at a pattern after taking successive ones. I could just show it on the screen here in terms of following factorial, but anyways, we have fractions here, so we're going to use gamma functions instead of factorials, and this will simplify. I also factored out some extra constants and also was able to rewrite the initial term as the k equals 0 term, so this is just one sum here. And now, again, similar to how I talked about for the Bring quintic video with, they said, oh, you need to split it into a separate finite sum of hypergeometric functions using Gauss's multiplication theorem. That is not actually true, or I don't know, that is an overcomplicated way, and you do not need to do that at all. And it was annoying that they even mentioned that because it misdirected me for a while. But what you actually need to do is to split it. You're going to split it into n sums using residue classes mod n, basically partitioning the indices to the different remainders when you divide by n, the numbers that give those remainders, right? So we're going to split by, so we're going to have k, we're going to have k to be nk plus j, where j goes from 0 to n minus 1. Basically, for example, if n was 2, this just splits between even and odd indices. So this is just now all the 1's mod n. And so we're going to get the following. Now we have this form, and now you see over here, the reason why we did this is because if you would originally take the ratio, the consecutive ratio of nth terms over here, you would not be able to cancel the gamma functions right here, since everything is all over n, nothing is divisible on top, with respect to k at least over here. So you can't separate out just a nice integer difference. So you're not going to be able to turn that into those rational factors that we're looking for. But now over here, since we multiply by nk, then that will be able to cancel. And so when we look at consecutive ratios, we're going to have like mk plus n for the k plus 1 term, and the same thing with the rest of these gamma arguments, and it will be able to be turned into the rational form for generalized hypergeometric functions, and that's how we're going to get them. In fact, showing on screen here, this is the calculation here, is just, again, from like the end of the quintic video, a little bit longer, and you get these products because it's like arbitrary size, n plus m and such. But anyways, if you look at those patterns of the factors that we get at the end, we can rewrite it at the following hypergeometric function. So this is the expression for the hypergeometric function. Again, it's kind of long because you have these arbitrary length parameters. But yeah, as we followed, it gave the proper structure from the ratio that we checked. And also here I'm going to show on screen when you want to back sub back to get x from our initial substitution, and also what t was written in terms of a and b. And now to get the rest of them, all we have to do is rearrange the equation. We're going to rearrange the equation. We're going to start from y equals n plus m is equal to y to the n minus t. So what we're going to do is just divide both sides by, we're going to divide both sides by y to the n. All right. Now we have this part canceling out. So what we're going to get is, now we have y to the m is equal to 1 minus t over y to the n. Now you see we have y to the m instead, so you guessed it, what we're going to do is substitute z to be equal to y to the m, which means that we're going to need y to be equal to omega z to the 1 over m, where we have omega to be any of the mth roots of unity, okay? So now we're going to get the proper form. We have z is equal to 1 minus t over omega to the n times z to the n over m. And so now we have the proper form. Instead, the constant thing, or the expansion area, is around 1. We're going to do Lagrange reversion with f of z is equal to z to the minus n over m, and g of z is equal to omega z to the 1 over m. So we have as follows the remaining m solutions. Okay, and so this is what the expression is going to be. Now note over here, for the k minus 1 order derivative, you're actually going to have the reciprocal, right? This is going to be a negative power over here. And again, there's a similar thing where you're going to look at the patterns and you can get the nth derivative, put n is equal to k minus 1. You know, with the reciprocals, the derivative alternates signs. So over here, this is going to cancel with the minus 1 to the k. And we're going to simplify this. And so now, instead of splitting by the residue class is mod n. We have m in the denominator here, so we need to split by the residue classes mod n. So we're gonna have k change to mk plus j, where now we have j is equal from 0 all the way to m minus 1. And so this is going to be simplified as follows. So this is the following expression that we have now. And again, you just check the ratios properly, and we're going to get another set of the parameters for the hypergeometric function, which we can write and there we go. That is the full solution. And I will show again the back substituted form for the solutions in terms of x and a and b. There is one extra case we should consider, which is if m is equal to 1. So basically, the max degree and the middle term, they differ by 1. In the case that we have that, notice over here, you'll just have the x to the n plus 1 root. That will be the 1 from that contribution. We'll have just one term, one hypergeometric function, but notice that j is going to be 0. So this cancels. Then we have minus 1 over 1, which gives us a gamma of minus 1, which is undefined. It's a singularity, right? So that's a problem. However, we have by Vieta's formulas for the roots of polynomial equations that the sum of the roots, again, this is from 1 to n plus 1, the sum of the roots from j equals 1 to n plus 1 of xj is just the negative of the second to leading coefficient, so the minus a. So that means that we can solve for this last one, xn plus 1, in terms of minus a minus j equals 1 to n of xj. And these things are still calculated the same way as we showed before for the first batch. But this seems to be the only special case because there are no other issues with singularities if m is greater than 1, like the arguments will be strictly negative and fractional, or they will be strictly positive and well defined for the gamma function. As far as I can tell, let me know in the comments if I missed anything. Additionally, notice with our parameters over here that we have, and how for the Bring-Jerrard quintic in the last video, we would get a 4f3. We would get 4f3 hypergeometric functions, but here it would give us 6f5. So it seems that like every time you can cancel at most 2 pairs to reduce it. Basically, like if you have, a 3f2 a, b, c like this, and then a and c, these are all common because from the definition they're just the rising factorials, and they're also in the fraction, so you could just cancel these out and reduce it to a 2f1. So it's the same thing here, and it always seems to be exactly 2 pairs that you can cancel. I'm not entirely sure, but that's what it seemed from when I was testing. Speaking of testing, we can go through a couple of examples in Mathematica right now. So as we can see over here, we have it for the reduced Bring quintic 1 parameter form from the end of the quintic video over here. And if we calculate it, you see that we're going to get all the same hypergeometric functions as shown in that video, except for we have some extra gamma factors that didn't cancel out, but again, their arguments differ by an integer, and they'll just turn into some rational expression. And if you just double check, they're going to be the exact same expressions that we got in the last video for the quintic. Now here is another example. We have it with complex coefficients too, and it is overall of degree 8. And so I also did a numerical solution here, and we can actually check these with the built-in numerical solver right here. So list 2 is what we have, and the way we ordered it, you see that everything here matches up properly. So we know that the formula works by this, and of course with the proper reasonable way that we derived it. So I hope that you've enjoyed this video, and it was an interesting dive into that part that we kind of missed on the explanation for the Bring-Jerrard quintic in the last video. And yeah, it was interesting to look through. I hope to see you in a future video. Goodbye.